The greatest triumph of civilization is often seen as our mastery of heat. Yet our conquest of cold is an equally epic journey, from dark beginnings to an ultra-cool frontier. In the last 100 years, cold has transformed the way we live and work. Imagine supermarkets without refrigeration or frozen food, skyscrapers without air conditioning, hospitals without MRI machines or liquid oxygen. We take for granted the technology of cold, yet it has enabled us to explore outer space and the inner depths of our brain. And as we develop new ultra-cold technology to create quantum computers and high-speed networks, it will change the way we work and interact. By the late 19th century, the ultimate extreme of cold had a number, minus 273 degrees Celsius, and a name, absolute zero. A frontier so enticing that rival physicists from all over Europe began a race towards this absolute limit of cold. It was a high-stakes pursuit, one that continues even now as we explore a strange quantum world where fluids appear to defy gravity and electricity flows freely without resistance. The race for absolute zero. Up next on Nova.
Major funding for NOVA is provided by David H. Koch and
Discovering New Knowledge. HHMI.
Major funding for Absolute Zero is provided by the National Science Foundation, where discoveries begin. Additional funding is provided by the Alfred P. Sloan Foundation to portray the lives of men and women engaged in scientific and technological pursuit. Major funding for NOVA is also provided by the Corporation for Public Broadcasting and PBS viewers like you. Thank you.
A century ago, Antarctic explorers were pushing further and further towards the coldest place on Earth, the South Pole, where temperatures can plummet to minus 80 degrees. The competition to reach this goal was matched by a less publicized but equally daunting scientific endeavor, the attempt to reach the coldest point in the universe, absolute zero. Was it possible to attain this ultimate limit of temperature, minus 273 degrees Celsius? Only in a laboratory, by liquefying gases, could scientific adventurers take the first steps towards this holy grail, a place where atoms come to a virtual standstill, utterly drained of all thermal energy. Among the front-runners in the race towards absolute zero was James Dewar, a professor at the Royal Institution in London.
It will be the greatest achievement of our age.
In 1891, he gave one of his celebrated Friday night public lectures on the wonders of the supercold to celebrate the centenary of his great predecessor, Michael Faraday.
The descent to a temperature within 5 degrees of zero would open up new vistas of scientific inquiry, which would add immensely to our knowledge of the properties of matter.
James Dewar is a canny and I think very ambitious, practically minded Scottish scientist. He could really show both his colleagues and the fee-paying audiences some of the secrets of nature.
Take this rubber ball. It bounces well, I think you'll agree, But let's see what happens after a few seconds immersion in liquid oxygen.
Dewar invented a thermal insulated container to carry out his research, and scientists to this day still call it a Dewar flask.
Now, let's see what happens.
This phantasmagoric aspect of science always helped science to be accepted by the public. Though it is a little mystifying, it did play a role of having society, having the public accept that these weird people in the laboratories are doing truly interesting, if not magical things.
Dewar's dream was to take on the mantle of the Royal Institution's greatest scientist, Michael Faraday. "70 years earlier, Faraday had done experiments showing that under pressure, gases like chlorine and ammonia liquefy. He was curious to see if this method of pressurizing gases into liquids could be used for all gases. But some, what he called the permanent gases, oxygen, nitrogen, hydrogen, would not liquefy, no matter how much pressure he applied. So he abandoned this line of research.
Faraday's was a mind full of subtle powers, of divination into nature's secrets. And although unable to liquefy the permanent gases, he expressed faith in the potentialities of experimental inquiry. The lowest point of temperature attained by Faraday was minus 130 degrees centigrade.
It was not until 1873 that a Dutch theoretical physicist, van der Waals, finally explained why these gases were not liquefying. By estimating the size of molecules and the forces between them, he showed that to liquefy these gases using pressure, they each had to be cooled below a critical temperature. At last he had shown the way to liquefy the so-called permanent gases was to cool them. Oxygen was first, and then nitrogen, reaching a new low temperature of almost minus 200 degrees centigrade.
Only the last of the permanent gases remains to be liquefied. Hydrogen, in the vicinity of minus 250 degrees centigrade. It will be the greatest achievement of our age, a triumph of science.
Dewar was determined to be the first to ascend what he called Mount Hydrogen, but he was not alone. The competitor Dewar feared most was a brilliant Dutchman, Heike Kamerlingh Onnes.
Kamerlingh Onnes was younger than Dewar, and to a certain extent looked up to the Scotsman as his senior. Dewar didn't have the same, if you'll pardon the expression, warm feelings towards his rival in the race for cold.
Dewar recognized that Kamerlingh Onnes had a new radical approach to science and was planning an industrial-scale lab.
When Onnes took over the physics laboratory in Leiden, he was only 29 years old. And, well, he gave his inaugural address here in this lecture room, the big lecture room of the Academy building of Leiden University. And it was all there. He was explaining what to do in the next years. And he was talking about liquefying gases, making Dutch physics famous abroad. And, well, it was amazing how far-sighted all those visions were.
Kamerlingh Onnes's lab was more like a factory. He recruited instrument makers, glassblowers, and a cadre of young assistants who became known as Blue Boys because of their blue lab coats. Later, he set up a technical training school, which still exists to this day. Dewar and Onnes could not have been more different. Dewar was very secretive about his work, hiding crucial parts of apparatus from public view before his lectures. Onnes, on the other hand, openly shared his lab's steady progress in a monthly journal. Onnes was the tortoise to Dewar's hare.
In the case of Dewar, you had a brilliant experimenter, a person who could actually build the instruments himself, and a person who really believed in the brute force approach, and that is, have your instruments, set up your experiment, and try as hard as you can, and then you'll get the results you want to get. In the case of Kamelichones, you have a totally different approach. He's the beginning of what later on was known as big science.
Unlike Dewar, Onnes thought detailed calculations based on theory were vital before embarking on experiments. He was a disciple and close friend of van der Waals, whose theory had helped solve the problem of liquefying permanent gases. Though their approaches were different, Kamerlingh Onnes and Dewar used a similar process in their attempts to liquefy hydrogen. Their idea was to go step by step down a cascade, using a series of different gases that liquefy at lower and lower temperatures. By applying pressure on the first gas and releasing it into a cooling coil submerged in a coolant, it liquefies. When this liquefied gas enters the next vessel, it becomes the coolant for the second gas in the chain. When the next gas is pressurized and passes through the inner coil, it liquefies and is at an even lower temperature. The second liquid goes on to cool the next gas, and so on. Step by step, the liquefied gases become colder and colder. Each one is used to lower the temperature of the next gas sufficiently for it to liquefy. In the final stage, where hydrogen gas is cooled, the idea was to put it under enormous pressure, 180 times atmospheric pressure, and then suddenly release it through a valve. This would trigger a massive drop in temperature, sufficient to turn hydrogen gas into liquid hydrogen at minus 252 degrees, just 21 degrees above absolute zero.
Here was the risky bit, because his apparatus was going down in temperature, getting very, very cold, so very fragile, quite easy to fracture, while at the same time the pressures he was working at were very, very high, so the possibility of explosion. He took the most amazing risks, both with himself, he was a lion of a man in terms of courage, and with those around him. All the equipment he was working with could have crumbled or blown up, and more than occasionally it did.
Dewar had many explosions in his lab. Several times, assistants lost an eye as shards of glass catapulted through the air.
In the notebook, he actually jots down many details of what happened in the apparatus, but not what happened to his assistants. So somehow you get the impression that apparatus is more important than the assistants.
Over in Leiden, Onnes was facing anxious city officials who were so worried about the risk of explosions that they ordered the lab to be shut down. Dewar wrote a letter of protest on behalf of Onnes. But the Leiden lab remained closed for 2 years.
Well, Onnes had to wait and to wait and to wait. Dewar was already starting with liquefying hydrogen, and well, Onnes had the apparatus to do so too, but it just couldn't start, so we had lost the battle before it was even begun.
The year is 1898. Dewar has been working on trying to liquefy hydrogen for more than 20 years, and he's finally ready to make the final assault on Mount Hydrogen.
By using liquid oxygen, they brought down the temperature of the hydrogen gas to minus 200 degrees Celsius. They increased the pressure till the vessels were almost bursting, and then opened the last valve in the cascade.
Shortly after starting, the nozzle plugged, but it got free by good luck. And almost immediately drops of liquid began to fall, and soon accumulated 20 cubic centimeters.
Dewar had liquefied hydrogen, the last of the so-called permanent gases. To prove it, he took a small tube of liquid oxygen and plunged it into the new liquid. Instantly, the liquid oxygen froze solid. Now he was convinced. He had produced the coldest liquid on Earth and had come closer to absolute zero than anyone else.
Dewar thought that he had done the most amazing feat of science in the world, that he would be immediately celebrated for it and get whatever prizes there were available. And that didn't happen.
I think for Dewar, it was the ambition of a mountaineer. You've climbed the highest mountain peak that you can see in the range around you, and just as you get to the top of the peak, there's an even higher mountain just beyond.
That new mountain was helium, a recently discovered inert gas that was originally thought only to exist on the sun. Van der Waals' theory predicted helium would liquefy at an even lower temperature than hydrogen, at around 5 degrees above absolute zero. Now, all Dewar had to do was obtain some. It should not have been difficult. The two chemists who had discovered the inert gases, Lord Rayleigh and William Ramsay, often worked together in the lab next door. Unfortunately, Dewar had made enemies of both of them by refusing to collaborate and belittling their achievements, so they had no desire to share their helium.
Camerlingionis was faced with the same problem as Dewar, which is, where can I get a supply of helium gas? And he actually asked Dewar to try and collaborate with him, too. And Dewar said, I'm having such a problem getting the gas by myself, I can't possibly give you any. I'd like to, but I can't.
Eventually, each found a supply. But Onnes's industrial approach paid dividends. After 3 years, he had amassed enough helium gas to begin experiments. The tortoise was beginning to pull away from the hare. At the same time, Dewar was running out of resources. To make matters worse, a lab assistant turned a knob the wrong way, releasing a whole canister of helium into the air. For 6 months, the lab couldn't do any work.
At one point, Dewar writes to Camerlingionis telling him that he's not in the race anymore. He thinks that the problems for liquefying helium are such that he's not able to complete the job.
The battlefields of science are the centers of a perpetual warfare in which there is no hope of a final victory. To serve in the scientific army, to have shown the initiative, is enough to satisfy the legitimate ambition of every earnest student of nature. Thank you.
In the summer of 1908, Onnes summoned his chief assistant Flim from across the river. They were finally ready to liquefy helium. At 5:45 on the morning of July the 10th, he assembled his team at the lab. They had rehearsed the drill many times before. Leiden was a small university town, and the word quickly spread that this was the big day. It took until lunchtime to make sure the apparatus was purged of the last traces of air. By 3 in the afternoon, work was so intense that when his wife arrived with lunch, he asked her to feed him so he didn't have to stop. At 6:30 in the evening, the temperature began to drop below that of liquid hydrogen. But then, it seemed to stick.
Honest doesn't know why this is. And a colleague comes in and he suggests that that means maybe they've actually succeeded and they don't even know it yet. So Honest takes an electric lamp type thing and he goes underneath the apparatus and looks, and sure enough, there in the vial is this liquid sitting there quietly. It's liquefied helium.
They had reached minus 268 degrees Celsius, just 5 degrees above absolute zero, and finally produced liquid helium. This monumental achievement eventually won Onnes the Nobel Prize. When James Dewar heard that he had lost the race to Kamerlingh Onnes, it reignited a festering resentment. Dewar berated his long-suffering assistant Lennox for failing to provide enough helium. Only this time, Lennox had had enough. He walked out of the Royal Institution, vowing never to return until Dewar was dead. And he kept his word. For Dewar, it was the end of his low-temperature research. James Dewar's dream of reaching absolute zero was over. Although he had won the first race to liquefy hydrogen, it never attracted the same accolades as liquefying helium. He abandoned low-temperature physics and moved on to investigate other phenomena, such as the science of soap bubbles.
I think it's really impressive how often scientists do seem to be driven by the spirit of competition, by the spirit of getting there first. But what's really fascinating about these races, the race for absolute zero, is that the goalposts move as you're playing the game. The race in science is not for a predetermined end, and once you're there, the story's over, the curtain comes down. That's not at all what it's like. Rather, it turns out you find things you didn't expect. Nature is cunning, as Einstein would have said, and she is constantly posing a new challenge, unanticipated by those people who start out on the race.
This is just what happened in Leiden, as Onnes's team began to investigate how materials conduct electricity at very low temperatures. They observed in a sample of mercury that at around 4 degrees above absolute zero, all resistance to the flow of electricity abruptly vanished. Onnes later invented a word to describe this new phenomenon. He called it superconductivity.
We have a circular ring of permanent magnets which are producing a magnetic field. And now when we put a superconducting puck over it and give it a little push, the magnetic field repels the superconductor.
The magnetic field from the track induces a current in the superconducting puck, which in turn creates an opposite magnetic field that makes the puck levitate.
It produces a magnetic field like a North Pole against the North Pole, and that's why you have the repulsion.
As the puck warms up, its superconducting properties vanish, along with its magnetically induced field. For decades after its discovery in 1911, the underlying cause of superconductivity remained a mystery.
Every major physicist, every major theoretical physicist had his own theory of superconductivity. Everybody tried to solve it, but it was unsuccessful.
There were more surprises ahead. In the 1930s, another strange phenomenon was observed at even lower temperatures. This rapidly evaporating liquid helium cools until at 2 degrees above absolute zero, a dramatic transformation takes place.
Suddenly, you see that the bubbling stops, and that the surface of the liquid helium is completely still. The temperature is actually being lowered even further now, but nothing particularly is happening. Well, this is really one of the great phenomenon in 20th century physics.
The liquid helium had turned into a superfluid, which displays some really odd properties.
Here I have a beaker with an unglazed ceramic bottom of ultrafine porosity.
Ordinarily, this container with tiny pores can hold liquid helium. But the moment the helium turns superfluid, it leaks through.
We call this kind of flow a superflow.
Superfluid helium can do things we might have believed impossible. It appears to defy gravity. A thin film can climb walls and escape its container. This is because a superfluid has zero viscosity. It can even produce a frictionless fountain, one that never stops flowing. Superfluidity and superconductivity were baffling concepts for scientists. New radical theories were needed to explain them. In the 1920s, quantum theory was emerging as the best hope of understanding these strange phenomena. Its central idea was that atoms do not always behave like individual particles. Sometimes they merge together and behave like waves. They can also be particles and waves at the same time. Even for great minds like Albert Einstein, this strange paradox was hard to accept. In 1925, a young Indian physicist, Satyendra Bose, sent Einstein a paper he'd been unable to publish. Bose had attempted to apply the mathematics of how light particles behave to whole atoms. Einstein realized the importance of this concept and did some further calculations. He predicted that on reaching extremely low temperatures, just a hair above absolute zero, it might be possible to produce a new state of matter that followed quantum rules. It would not be a solid or liquid or gas. It was given a name almost as strange as its properties: a Bose-Einstein condensate. For the next 70 years, people could only dream about making such a condensate, which has never been seen in nature.
Matter can exist in various states. Atoms at high temperature always form gases. If you cool the gas, it becomes a liquid. If you cool the liquid, it becomes a solid. But under certain circumstances, if you cool atoms far enough to extremely low temperatures, they undergo a very strange transformation. They undergo an identity crisis. So let me show you what I mean by an identity crisis. When you go to low temperatures, the quantum mechanical properties of the atoms become important. These are very strange, very unfamiliar to us, but in fact, each one of these atoms starts to display wave-like properties. So instead of points like that, you have little wave packets like that moving around. It's really difficult for me to explain just why that is, but that's the way it is. Now, as you go to very low temperatures, the size of these packets gets longer and longer and longer. And then suddenly, if you get them cold enough, they start overlapping. And when they overlap, the system behaves not like individual particles, but particles which have lost their identity. They all think they're everywhere. This little wave packet over here can't tell whether it's this one or that one or that one or that one or that one or that. It's there and it's there and it's there. They're all in one great big quantum state. They're all overlapping. They're all doing the same thing. And what they're doing, to a good approximation, is they're simply sitting at rest. This Bose-Einstein condensate is very difficult to imagine or to visualize. I can imagine what it's like to be an atom running around gaily, freely, bouncing into things, sometimes going fast, sometimes going slow. But on the Bose condensate, I'm everywhere at once. I've lost my identity. I don't know who I am anymore. I'm at rest, and all the other atoms around at rest, but they're not other atoms around. We're all just one great big quantum system. There's nothing else like that in physics, and certainly not in human experience. So just to think about this causes me wonder and confusion.
Dan Kleppner and his MIT colleague Tom Graytak began to try to make a Bose-Einstein condensate in hydrogen.
As we started out the search for Bose-Einstein condensation, our enthusiasm grew because hydrogen seemed like such a wonderful atom to use. It had everything going for it. It had its light mass. That means that the atoms will condense at a higher temperature than other atoms would. The atoms interact with each other very, very weakly. All the signals seem to be pointing to the fact that hydrogen was the atom for getting to Bose-Einstein condensation.
Kleppner's idea was to cool the hydrogen atoms by making use of their magnetic poles. He used a strong magnetic field to create a cluster of atoms in a cold trap. Unfortunately, sometimes one atom flipped another, which triggered a release of energy that raised the temperature.
It was a frustrating time for us because our methods were so complicated, we were having a hard time moving forward.
Now others decided to take up the challenge. Two physicists from MIT met in Boulder, Colorado, and came up with a different approach to the problem. Rather than focusing on the lighter atoms of the periodic table, they hit upon the idea of using much heavier metallic atoms, like rubidium and cesium. But would using these giants enable them to reach closer to absolute zero?
The idea in the field in those days was that the light things like hydrogen and lithium would be easier. And there were some good reasons for thinking that, but we had other ideas.
Yeah, sort of gut intuition in some sense.
Their plan was to use a laser beam to cool the atoms, a technique that had already been tried by physicists at MIT. Lasers are usually associated with making things hot. But if they are tuned to the same frequency as atoms traveling at a particular speed, lasers can cool them down. When the stream of light particles from the laser hits the selected atoms in the gas cloud, they slow down and become cold. Laser cooling was a new tool that had the potential to reduce the temperature of a gas to within a few millionths of a degree of absolute zero. But Cornell and Wyman were not the only ones excited by this prospect. A new scientist had arrived at MIT.
It was in late 91 or early 92 that we had an idea how a different arrangement of laser beams would be able to cool atoms to higher density. And it worked. And this was really a trigger point. I will never forget the excitement in those group meetings when we discussed what do we next. Because with higher density, there are many things you can do. Could we now push to Bose-Einstein condensation? You see, well, lots of cables and electronics.
All the resources of Ketterle's lab were redirected to make a condensate in sodium atoms.
And right here, this is an atomic beam oven. What is wrapped in tinfoil is a little vacuum chamber where we heat up metallic sodium so the metallic sodium melts and evaporates. And it's ultimately the sodium vapor, the sodium atoms, which we tried to Bose-Einstein condense.
MIT, Boulder, and several other labs were chasing the same goal. It had echoes of the race to produce liquid helium almost a century earlier.
As I tell my students today, anything worth doing is worth doing quickly because science moves on and we're all mortal and you want to do things.
While MIT was installing its sophisticated lasers, Carl Wyman's approach was small is beautiful.
In some cases, he was ripping open old fax machines and taking out the little chip inside that made the laser and showed that you could take these lasers and put them into a home-built piece of apparatus, stabilize the laser, and use them to do spectroscopy and laser cooling.
This is actually our first, what's called the vapor cell optical trap. You can see it's kind of this old cruddy thing, pulled together glass, where we could send laser beams in from all the different directions and have just a little bit of the atoms we wanted to cool.
As well as bombarding the atoms with lasers, they also trapped them in a strong magnetic field.
We would try this sort of magnetic trap, that sort of magnetic trap, this sort of imaging, that sort of imaging, that sort of cooling. All those things we could do without building a whole new chamber each time. We tried literally 4 different magnetic traps in 4 years, instead of having a 3 or 4 year construction project for each one.
By being fast and flexible, the Boulder Group hoped to beat their old lab at MIT. But MIT had its own plans.
There was a sense of competition, but it was what I would call friendly competition. I mean, can you imagine 2 athletes? They are in the same training camps, they help each other, they even give tips to each other. But then, when it comes to the race, everybody wants to be the first.
The rival groups were both using magnetic trapping and lasers to cool their atoms. But for the final push towards absolute zero, to turn these atoms of gas into the quantum state Einstein had predicted, they needed one more cooling technique: evaporative cooling.
It's just like with this coffee. The steam coming off the coffee is the hottest of the coffee molecules escaping and carrying away more than their fair share of energy. In the case of the atoms, we keep the atoms in a sort of magnetic bowl, and we confine the atoms there. They zoom around inside the bowl, and then the hottest ones have enough energy to roll up the side of the bowl and fall over the edge, slop over the edge, taking away with them much more than their fair share of energy, and the atoms that remain have less and less energy, which means they move slower and slower and start to cluster near the bottom. And as that happens, we gradually lower the edges of the magnetic trap, and always so there's just a few atoms that can escape, until finally the remaining atoms cluster near the bottom of the bowl, huddled together. They get colder and colder and denser, and eventually in this way evaporation forces the Bose-Einstein condensation to occur.
The race to produce a Bose-Einstein condensate was intensifying.
At every major meeting, Eric Cornell and I gave talks or talked to each other. We were keenly aware that we were both working towards the same goal.
In June 1995, the Boulder Group was working round the clock, knowing that MIT and several other labs were also poised to produce the first condensate. An official visit from a government funding agency was the last thing they needed.
We didn't want to close down the lab or clean up our lab or put up posters. We wanted to work very hard. So the senior dignitaries in the three-piece suits and so on came in to the lab, and we left the lights off, and everyone continued to work. And I made them keep their voices down and talked to them rather in a hurried way, and then sort of shuffled them out the door. And they all had a slightly puzzled look on their face, because it probably had never happened to them before in the history of being a visiting committee, that they were treated with as little pomp. And later I actually met one of the guys who said, I suspected something was up that day, because otherwise you never would have dared to do that.
June the 5th, 1995, turned out to be a big day in the history of physics. The Boulder Group seemed to have made what Einstein had theorized 70 years before, a Bose-Einstein condensate.
Our first reaction was, wait, we got to be careful here, you know. Let's think of all the different knobs we can turn, checks we can make, and so on, to see if this really is Bose-Einstein condensation.
condensate is sort of like a vampire. If the sunlight even once falls on it, it's dead. And so its realm is the realm of the dark. But we can take pictures of them because we strobe the laser light really fast, and even as the condensate's dying, it casts a shadow, and the shadow is frozen in the film.
At a temperature of 170 billionth of a degree above absolute zero, Wyman and Cornell created a pure Bose-Einstein condensate in a gas cloud of just 3,000 atoms of rubidium, the first in the universe, as far as we know.
One of the first things you need to understand about Bose-Einstein condensation is how very, very cold it is. Where we live at room temperature is far above absolute zero on this scale. Imagine that room temperature is represented by London, thousands of kilometers from here. Then on that scale, if we imagine right here where I'm standing in Boulder is absolute zero, the coldest possible temperature, then how close are we to absolute zero? If we think of London as being room temperature and right where I am is absolute zero, then Bose-Einstein condensation occurs just the thickness of this pencil lead away from absolute zero.
Within months of the Boulder Group's success, Wolfgang Ketterle produced an even larger condensate from 500,000 sodium atoms, slowed down to a virtual standstill, causing their wave functions to overlap to produce an entirely new state of matter. At last, quantum mechanics was more than just a theoretical construct. It was something that could be seen with the naked eye. Cornell, Ketterle, and Wyman shared the Nobel Prize for Physics in 2001.
One of the things the Nobel Prize means, and the ceremony means, that everybody remembers Eric's the person who forgot to bow to the king.
There was a breakdown of protocol on my part. There was no excuse because they actually drill us to. It's more like you have a series of rehearsals practicing how to bow to the king, and I somehow managed to bollocks it up at the last possible moment. And I thought maybe, Carl, who came after me, would make the same mistake, and then no one would figure it out. But no, he was perfect.
I heard about the Nobel Prize when I was woken up by a telephone call, which was at, I think, 5:30 in the morning. So you wake up, you go to the telephone, and somebody tells you, congratulations, you've won the Nobel Prize. You're still tired, your brain is not fully functional, but you realize this is big, and what you feel is pride for MIT, your collaborators, for yourself. It's wonderful to see that your work gets recognized and acknowledged in this way.
Like any great adventure, the pursuit of science offers no guarantee of success. But for the godfather of ultra-cold atoms, persistence eventually paid off. In 1998, after 20 years of struggling to obtain a condensate in hydrogen, Dan Kleppner finally succeeded. For a few fleeting moments, his dream came true.
Of course, we were delighted, and I think everyone was delighted, because we'd been working on it for so long. It's kind of embarrassing to have this group which helped start the work and was working away there fruitlessly while everyone was enjoying success. When we got it, everyone was happy.
To see that an effort which lasted for 20 years, which took so much patience, frustration, and tenacity, to see that succeed is just emotional, it's liberating. I will never forget this standing ovation which Dan Kleppner received at the Varenna Summer School when he announced Bose-Einstein condensation in hydrogen.
Everybody just got up and it was sort of like an opera where everybody just cheered and people were crying, and because everybody realized that they had finished the race, but too late, and it wasn't going to work out, but in some sense they had really stimulated the whole field, so it was a very moving moment.
For the pioneers who had realized Einstein's dream and created condensates, it was the end of an extraordinary decade of physics. Now there was a new challenge, to work out what to do with them. At Harvard, a Danish scientist, Lena Howe, had the idea of using a condensate to slow down light.
We all have this sense, light is something that nothing goes faster than light in vacuum. And if somehow we could use this system to get light down to, to a human level, I thought that was just absolutely fascinating.
Lena Howe created a cigar-shaped Bose-Einstein condensate to carry out her experiment. She fired a light pulse into the cloud. The speed of light is around 186,000 miles per second, but when the pulse hits the condensate, it slows down to the speed of a bicycle.
So light pulse might start out being 1 to 2 miles long in free space. It goes into our medium. And since the front edge enters first, that will slow down. The back edge is still in free space. That'll catch up, and that'll create that compression. And it'll end up being compressed from 1 to 2 miles down to 0.001 micron, or even smaller than that. You could say, well, gee, it's easy to stop light because I could just set a laser beam into a wall and I would stop it. Well, the problem is you lose the information because it turns into heat. You can never get that information back. In our case, when we stop it, the information is not lost because that's stored in the medium. And then when we have time to revive it, the system has all the information to revive the light pulse and it can move on.
One day, ultra-cold atoms will probably be used to store and even process information. Even now, cold atoms are being turned into prototype quantum computers.
As a quantum mechanic, I engineer atoms. To make a computer out of atoms, you have to somehow get atoms to register information and then to process it. Why build quantum computers? Because they're cool, it's fun, and we can do it. Right? I mean, we actually can take atoms, and if we ask them nicely, they'll compute. That's a lot of fun. I mean, have you ever talked to an atom recently and had it talk back? It's great.
Yes, look at that.
Unlike ordinary computers, where each decision is based around a bit of information and is either a 0 or a 1, in the quantum world, the rules change.
At first glance, a quantum computer looks almost exactly the same. But quantum mechanics is weird. It's funky, okay? It's weird.
When you do quantum computing, you want to make this weirdness work for you.
So now let's look at our quantum bit, or qubit.
A qubit can not only be a 0 or a 1, it can also both be a
0 and 1 at the same time. It's almost like a form of parallel computation, but in a parallel computer, one processor does this, one processor does that. So you have two processors doing this and that. In a quantum computer, you have only one processor that's doing this and that at the same time.
Today, computers are limited in the amount of information they can handle by the heat and number of the circuits. Here, within a giant Dewar flask, lies a prototype quantum computer surrounded by its supercooled, superconducting magnet. In the future, quantum computing could be used to predict incredibly complex quantum interactions, such as how a new drug acts on faulty biochemistry, or to solve complex encryption problems like decoding prime numbers that are the key to internet security. Already, supercooled quantum devices are mapping the magnetic activity of the brain. Often, the promised benefits from a scientific breakthrough take a long time to emerge. Many predicted that by this century, energy-saving superconducting power lines and maglev bullet trains would be crisscrossing the continents. Perhaps as world energy supplies decline, these technologies, once seen as too costly, will start to take off. This weird quantum world is part of a new frontier opened up by the descent towards absolute zero. It's been a remarkable journey for scientists into unknown territories far beyond the narrow confines of Earth. On the Kelvin temperature scale, which begins at absolute zero, the temperature of the Sun is around 5,000 Kelvin. At 1,000 Kelvin, metals melt. At 300, we reach what we think of as room temperature. Air liquefies at 100 Kelvin. Hydrogen at 20. Helium at 4 Kelvin. The deepest outer space is 3 degrees above absolute zero. But the descent doesn't stop there. With ultra-cold refrigerators, the decimal point shifts 3 places to a few 1,000ths of a degree. And laser cooling takes it down 3 more places to a 1,000,000th of a degree, the temperature of a Bose-Einstein condensate. With magnetic cooling, we shift 4 more decimal places until we reach the coldest recorded temperature in the universe, created at a lab in Helsinki, 100 picokelvin, or a 1/10 of a 1,000,000th of a degree above absolute zero. So, will it ever be possible to go all the way, to reach the holy grail of cold, 0 Kelvin?
Getting to absolute zero is tough. Nobody's actually been there at absolute 0.000000 with an infinite number of zeros. That last little tiny bit of heat becomes harder and harder to get out. And in particular, the timescales for getting it out get longer and longer and longer, the smaller and smaller the amounts of energy involved. So eventually, if you're talking about extracting an amount of energy that's sufficiently small, it would indeed take the age of the universe to do it. Also, you actually need an apparatus the size of the universe to do it, but that's another story.
Absolute zero may be unreachable, but by exploring further and further towards this ultimate destination of cold, the most fundamental secrets of matter have been revealed. If our past was defined by our mastery of heat, perhaps our future lies in the continuing conquest of cold.
On NOVA's Absolute Zero website, enter a virtual lab and see how close you can get to absolute zero. Make your own temperature scale and more. Find it on pbs.org. Major funding for NOVA is provided by David H. Koch and
Discovering New Knowledge. HHMI.
Major funding for Absolute Zero is provided by the National Science Foundation, where discoveries begin. Additional funding is provided by the Alfred P. Sloan Foundation to portray the lives of men and women engaged in scientific and technological pursuit. Major funding for NOVA is also provided by the Corporation for Public Broadcasting and PBS viewers like you. Thank you.
Next time on NOVA, a powerful medical detective story.
Here are humans doing things that they're not meant to be doing.
Several children who walk on their hands as well as their feet.
In a way which no adult humans have walked for 2-3 million years.
What can we learn from one extraordinary family's fate?
This was potentially dynamite.
We're going to have to tease away this to find out what underlies this extraordinary phenomenon.
Family that walks on all fours. Next time on NOVA.
To order this NOVA program for $24.95 plus shipping and handling, call WGBH Boston Video at 1-800-255-9424.